Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Aidan McFord. Aidan completed his master's at the University of Bristol, where he worked on gold redox catalysis for cross-coupling reactions in the group of Dr. Chris Russell. He has since begun his PhD at Bristol, where he completed 3 rotation projects in the labs of Professor John Bauer, Dr. Beatrice Collins, and Professor Chris Willis. He then settled on the Collins group, where he's completing his PhD on the development of autonomous molecular motors. And from there, I'll hand the floor over to you, Aidan. Thank you very much for coming on today.
Hi Matthew, thank you for having me on Synthesis Workshop today. I'm really delighted to be able to present my work here and share one of the things that I've been looking at during my PhD, which is to investigate the steric effect of substituents by using a new computational approach, which builds on the A value and thus uses cyclohexyl rings. So, as many of us know, early on in our chemical careers, we're taught about the impact of steric effects and how they can really affect reactivity. For example, the steric environment of a ligand can impact the conversion to a particular product, and it can also impact the stereochemical outcome of a reaction. In a similar sense, the substituents that are placed on a molecule can affect its physical behavior and also have an impact in a reaction. So it's important to be able to quantify the size of a substituent or profile the size of a substituent in one way or another. One of the ways in which this can be done is with descriptors, and for example, geometric steric descriptors give a purely geometrical interpretation of the size of a substituent or of a molecule, and here we're going to focus on substituents. And they really treat atoms as fixed radius spheres of different sizes, and one example of a steric descriptor, which is purely geometric, is the cone angle, and that effectively takes a substituent, sticks it at a particular distance from a point, and then looks at the angle that that group subtends from that point. So one could imagine the larger the substituent, the wider angle it will subtend, and conversely, the smaller the angle, the smaller the group. Alternatively, there are different steric descriptors out there, including the percent varied volume, an alternative way of interpreting size, which is less geometric in nature, focuses on free energy steric descriptors. One such example is the A value, which effectively takes a substituent and places it on a cyclohexyl ring. And in solution, cyclohexyl rings can readily ring flip, and this changes the conformation of the substituent, here shown in blue, from axial to equatorial and vice versa. And this will exist as an equilibrium. The equilibrium ratio constitutes something that has been termed the A value, and the A value is effectively the energy difference between the substituent being axial and being equatorial. As when we are in the axial position, as shown on the left now, the substituent will undergo 1 free diaxial interactions with axial hydrogen atoms in the cyclohexyl ring, and this is unfavorable. This is some form of steric clash. And so the preference will generally be for the substituent to be equatorial, and the larger that substituent is, the larger the preference is for it to be in the equatorial conformation. So you can see a methyl group, for example, has an A value of 8.26 kilojoules per mole. This increases slightly to the ethyl group, which means an ethyl group has a slightly larger preference for being equatorial just because of its larger size. But interestingly, it's not that much bigger than a methyl group. And when we go up to isopropyl, again, there's a very small difference between ethyl and isopropyl versus methyl, and it's only once we look at the tert-butyl group that we see a significant difference in the preference for the substituent being equatorial. And the reason for this is that the A value doesn't capture the full steric size of the substituent. In the methyl group, we can imagine a bunch of axial conformers, as shown in the bottom left, which can interconvert. So I've labelled this hydrogen atom here in red. And no matter which way this bond rotates, all of the axial conformers are indistinct unless we actually label one of these hydrogen atoms, and they're thus all equal in energy. Conversely, when we see the ethyl group on the right, this conformation with the methyl group pointing inwards provides a lot of steric clash, and so the dominant conformation for the ethyl cyclohexane actually points the methyl group far away. This kind of conformational freedom in the substituent means that we don't capture the full size of the ethyl group, and it effectively can behave in a very similar manner to the methyl group. This also applies to isopropyl, where we don't really capture the full size of an isopropyl group. It's only once we get back to tert-butyl that we have a C3 symmetric group again, and no matter which way the tert-butyl points when it's in the axial conformation, we capture the full size effectively, and thus there's a large increase in A value. What we wanted to do was to be able to come up with a new steric parameter which could capture the size of a substituent at the point of attachment, but didn't have the same issues from conformational averaging, where actually we don't capture the size. And this really was Roger's brainchild. It was really interesting to see how all of this came about, and I was really glad to see the development of this project and be able to work on it. And effectively what Roger came up with was to consider a molecule where no matter which way a substituent points, it can't escape a certain number of interactions. And one molecule in which this is possible is with graphene, as shown here. So if we were to take the smallest unit of graphene, 13G as we're going to call it, and place a substituent in the middle, this substituent is axial to 3 cyclohexyl rings, and importantly it has 6 diaxial interactions with the upwards pointing hydrogen atoms. So no matter which way it points, it's always going to have some sort of steric clash. This means that we should be able to capture the full steric effect of a substituent close to where it's attached. Of course, we might want to consider a molecule where the substituent is now equatorial to 3 cyclohexyl rings, and we can do that with adamantane. Adamantane and graphene aren't conformers of one another. They're very distinct, different molecules, but what we can do is consider an equilibrium where the substituent is on the graphene and where it moves over to the adamantane. This is a purely hypothetical equilibrium, and so we can set it up computationally, and it looks something like this. So we can have our substituent on the left in the unfavorable axial position to all of these hydrogens, this ring fence of hydrogen atoms. And we can imagine breaking this carbon substituent bond and placing the substituent now in the adamantyl group. Just like with the preference in cyclohexane for the substituent to be equatorial, we have an energetic preference for that substituent in this new equilibrium to be on the adamantane. And this preference we're going to call delta GGA, and this is our new steric parameter which aims to capture the full steric size of a substituent. Importantly, because we're breaking and making bonds in this case, we're maintaining 2 different molecules where the substituent is attached to a quaternary center. So we're not going from, say, a quaternary to a primary or anything like this. There's minimal electronic impact. And what we'll see from some of the data is that we actually span a really large energetic range with our parameter, and this effectively means that we can have high confidence in the computational results, and much less error than comes in with calculations of things like A values. We also avoid the conformational issues that came up with the A value. So as you can see, and as I sort of mentioned earlier, an ethyl group on our graphene, no matter which way it points, it's always facing the diaxial interaction, and thus we're capturing the steric impact of that group. To explain kind of how we did this, it was purely computational, as this is a purely computational tool to appreciate the size of substituent. We modeled a range of adamantyl substituted molecules and graphene substituted molecules. These were optimized in Orca using a DFT method with dispersion correction. We also repeated our calculations for optimization and energies with a non-DFT method, and were reassured to see that both methods agreed with one another. And some of the substituents that we looked at included this set here. This isn't the full set, but it captures most of what we're looking at. So we had a range of alkyl groups, we had haloalkanes, silanes, halogens, a range of sp2 groups, and other attachments such as ethers and amines, amides, and boronic esters. Now, a lot of these groups are very different to one another, so we can't just compare the whole set. We have to draw out the trends between the appropriate substituents. A good example to show is with alkyl groups. So if we take the set methyl, ethyl, isopropyl, and tert-butyl, what we see is that unlike the A value before, where the size isn't captured and we have very similar A values between methyl and isopropyl, and a large jump once we get to tert-butyl, we actually have a near linear increase in energy for each methyl group added to the substituent, i.e. moving from methyl up to tert-butyl. And so we capture the steric impact of these groups quite well. Alternatively, as well, we looked at elongating the chain of the substituent. What we saw on going from methyl and bringing the chain up to an N-butyl was that, as you might expect, the delta G value increases once we get to ethyl, but as the chain gets longer, the average conformation keeps the rest of the chain away from the point of attachment and this ring fence of hydrogens that provide this repulsive interaction, and thus we don't have an increase in the delta G value as we get to a longer and longer chain, and this is something you would expect to see as well with an A value, is that the chain would be far enough away from the diaxial hydrogens that there would effectively be no increase in preference for axial versus equatorial. This can also be visualized here with a chem draw, where you can see quite clearly that the majority of the chain is away from this constricting force, which tends to go about 2 angstroms above the plane of graphene. And to exemplify this further, what we did was we took a tert-butyl derivatized acetylene, which is only really bulky quite far away from the point in which it's attached, and so we actually have a very small delta G value for the tert-butyl acetylene group, and that's because, as you can see, the 3 methyl groups are very far away from the graphene sheet and very far away from this constricting repulsive force of the hydrogen atoms. Of course, we wanted to be sure that our new parameter was purely steric in nature, and so what we did was look for electronic effects. We compared our delta G values against Hammett sigma m parameter data, and we saw no positive correlation, which tells us that there are no electronic factors that play into our steric parameter. We also compared our data against a range of other steric parameters. One of them is a linear free energy relation called Taft-Dubois parameter, and we saw a good correlation there with our data. So this again lines up with it being steric in nature, and to reiterate that, what we did was we compared our data to cone angles and solid angles, which, as mentioned at the beginning, are purely geometric in nature, and what we found was a good correlation between both sets of data and our delta G value. So in conclusion, we have developed this delta G parameter which provides a view of substituent steric effects close to the point of attachment, and there's an easy computational tool where one can look at the steric impact of any given substituent by just calculating this equilibrium between the graphene and adamantane substituted molecules. Our parameter provides an improvement on the A value in terms of size at the point of attachment, because conformation or averaging issues are avoided, and it provides a symmetrical constriction force around the substituent to do this. The data can be easily interpreted, and it can be done so with high confidence, as we have an energy range that spans over 140 kilojoules per mole, and our parameter is in good agreement with other steric parameters such as the Taft-Dubois, cone angle, and solid angles. And with that, I'd like to acknowledge all the people that I worked on this project with, so in particular Roger Alder, and this was really his conception, and it was really great to be able to work with him, but of course it was great to work with Professor Craig Butts and Dr. Natalie Fay, one of my supervisors. On top of that, I'd also like to thank my other PhD supervisor, Beatrice Collins, and both the Collins and Fay groups. I'd like to thank the University of Bristol for my PhD studentship, and also the EPSRC for funding, and the Bristol Chemical Synthesis CDT. If you have any questions, I'm happy to answer those. If you take my email or LinkedIn, I'll get back to you when I can. And I'd like to thank Matthew for having me today and allowing me to share the work on Synthesis Workshop, which I think is a great platform. Thank you.
Thank you for tuning in for this Research Spotlight episode, and thank you to Aidan for a very interesting talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.